Good morning, Year 12. Hello. It's Thursday morning. Can you believe it? Wow, this week's gone fast, guys. It's gone fast. It's nice having people here. I've got Dana, got Dat. Yay. I'm trying to pause my other laptop. Hello. I've got Dana, I've got Dan, I've got Tenzi, I've got Nikita, I've got Kayun. Doing well. Let's do the register. Got Dat. Don't mean to do that again. Got Dat, got Kayun. Got Tenzi, got Nikita, got Dat, got Dana, doing well. Got Ivan, hey. Got Ivan, got Jasmine, whoop, whoop, doing well. You guys are always so prompt. Good job, guys. It's nice to see you. How's everyone coping this morning? Is everyone looking forward to 2 weeks break? I bet they are. I know that I am. Oh, man. Can't wait. Can't wait. I've got a feeling that there's going to be a few people who are late. Oh, Sherlyn. Hi, Sherlyn. Good. Great to see you. Mika's here. Yay. We're doing really well. Only 3 people missing now, the usual late arrivals. We've got Ria, we've got Ben, we've got Emma. Got a couple of people missing. Okay, just to start the process, guys. You can see my learning objectives, and they're all understands, tricky ones. Yeah, we've got understand free radical substitution ozone problem. So we'll do ozone today. Now, can I just point out, by the way, that ozone strictly isn't actually on your Edexcel specification. But I have come across one question on an Edexcel paper that included it. It was a relatively straightforward question, but I want to teach it anyway because of that. When I saw it, I was like, that's not really meant to be there, but I can understand what they were doing. They were looking to see that you could apply your understanding of initiation, propagation, termination, and looking to see if you could apply it to a scenario that you'd never seen before. And I was like, oh, it's a bit mean that they've done that, but Edexcel seems to do this. So I'm very aware of it. So I'm going to run that one. I'm then going to do understand EA major minor products. So I haven't done electrophilic addition with you guys, because it's on the other side. It's on unit 1. Hey, Ria, good to see you. Ria's arrived. Yay. Good morning. Just waiting for Ben and waiting for Emma. God, slackers. Slackers. I have only started 2 minutes ago. I can't really complain. You guys are amazing. You guys have just been so brilliant. You've turned up to all my lessons. It's like I'm made up. It's made me really, really, really proud to see you guys all attending. I'm assuming it's not because, of course, my lessons are so entertaining. I'm assuming you're turning up because you're bored. I could totally see that. Okay, so no Ben, no Emma. What I'll do is I'll mark them guys as absent, and then I'm going to crack on. I may as well. Is this, oh, I just suddenly realized something. Is this, guys, this is our last lesson before Easter. This is it, last one. Guys, right, that has a consequence that I didn't really realize, because we finished unit 2. We've done it, which means as soon as we get back, you guys are going to have a mock. So I need you guys to start looking at papers. And I'm also worried about unit 3, of course. We haven't really done specific unit 3 content. We just realized it's kind of rolled into unit 1 and unit 3 teaching. I always mention it whenever it comes up. But I do need you guys to be having a look at those exam papers. And over Easter, I'll probably run some revision webinars. I'll do some revision webinars with you guys on paper 2 and on paper 3. So I need to set some as homework. And you guys really do need to do these. You guys are in the unfortunate situation of being trapped in the middle of this whole coronavirus thing, because the year 13s, of course, aren't going to sit their exams, and the year 11s aren't going to sit their exams, but you guys are going to be trapped in this really awkward intermediate, which is you guys are going to end up having to do something strange, like doing them in January or something. It's all going to be a bit of a mess. We will sort it all out, but I don't want you to think that you guys don't have to do the work. We really do. And in fact, it's more important that we focus on trying to get this like really up to a good standard. And I don't want you guys to just like slack off and not, oh, Ben's just turned up. And just lose all the stuff that I've done with you. Yeah, it is really important for you guys especially. Okay, so since the only person now that's missing is Emma, I'm gonna crack on. Sherlyn, if you could do me a favor and just send her a message, that'd be really nice, be useful. Okay, so let's share screen. Let's share a screen. Share a screen, me and you. Okay, let's go into that. And so you guys can now see my screen. Right, so one of the things that I wanted to do today was, I know my learning objectives are looking at these particular problems as regards to the mechanisms, but I just wanted to show you guys a question that was on an A-level paper that really highlights that you can't just teach organics. You can't just do this. And this is why, because it says alcohols undergo dehydration in the presence of concentrated phosphoric acid via a carbocation intermediate to form alkenes. Complete the mechanism for the conversion of, and it gives you a mechanism that you guys are not taught. And that is really tough, folks. That is just showing that they can do this. I can't just teach you guys mechanisms out of a textbook and say, guys, go away and learn this, because then they're going to throw these kind of questions. And if you don't know how to handle it, it's going to leave you in a really difficult spot, because that's 4 marks, and it's going to be 4 marks that's a whole grade boundary. And I really, really need to be making sure that you guys are understanding our mechanisms from top to bottom, and you're able to build them rather than doing this like rote learning. It's not good chemistry. I'm going to come back to this question, by the way, at the end of the webinar. So today's lesson, primarily, we're going to go through all those tricky, problematic bits that everyone always finds challenging in mechanisms. It's always the really difficult bits. And so the first thing we're going to do is I'm going to be focusing on FRS. And we're going to be focusing on what's called the ozone problem. So the first thing I just need to talk to you guys about what the ozone is. So we know that our planet, our atmosphere, so this is our planet here. Yeah, there's our planet. And this is our atmosphere. Here's our atmosphere. And our atmosphere actually has layers. And those layers include the ground one, which is this, the bottom layer is called the troposphere, troposphere. Yeah, it's called the troposphere. Tropics, that's where it comes from. This is the warm, this is where 90% of the atmosphere actually exists. As you then move away from the planet, it gets thinner. You probably know that. The troposphere, I think it's tropo. I haven't done this in a while. I haven't done the structure of the atmosphere in like 2 years, so I probably ought to do a bit of checking. You guys can check me on these words. I'd really appreciate the support in that. Just checking, just Googling perhaps. Dat, you can help me out with that perhaps. You're usually pretty good at that. Okay, after the troposphere, the one above the troposphere is called the stratosphere. This is then called the stratosphere. So this is upper atmosphere. Now you've got like the last 5% in this one. And then you've got, then I think it's the ionosphere after that, but that's a big one. And the point I'm trying to make is, although I don't actually think it's the ionosphere, but the point I'm trying to make is just above the stratosphere. Above this, there's a layer. So this is what I want you to realize, that this is really upper atmosphere. This is really, really high up. And there's a rather skinny layer. And this skinny layer is called the ozone layer. It's called the ozone layer. And ozone is O3. This is the name given to oxygen when it's in a 3. And you guys may have come across this with dot and crosses. Edexcel have used ozone for dot and cross at times, which is a bit of a dot and cross diagrams for Edexcel are very tough. They're very challenging. And so O3 is a rather, you guys never talk about this. In fact, in GCSE, I deliberately avoid it because I'm trying to get students to recognize oxygen as O2. So then when we throw in ozone in AS chemistry to say, oh, by the way, there's actually O3, and people go, what? It's a bit of a nightmare. Just to show you what ozone looks like. By the way, number one is it's toxic. Ozone is actually quite a toxic chemical. So luckily it doesn't exist at ground level. It only exists right up in the upper atmosphere, past the stratosphere. It's actually, I think it's actually inside the top end of the stratosphere. And so what does ozone actually look like? Ozone looks like this. We've got an oxygen atom. Now we know that oxygen's usually O2 is diatomic and it has a double bond like this. Here's oxygen. There's oxygen. Everyone recognizes that one, O2. And then here's a third oxygen atom. Try and make that a similar size to the others. There we go, I'll do. Here's another oxygen atom. Now, oxygen does something rather interesting now, because in order to be able to make a bond, it can do a dative. So what there is now actually a bit of a reshuffle of electrons. This one moves down to here, and then you can actually form a dative at that point. Trying to make them the similar size. So we can actually form a dative bond there. Now, when it does this, it's nice to talk about charges, you see, because this has been done at Edexcel as a method of being able to see if people understand the whole idea of curly arrows. Yeah? So in terms of what's happening here, we could argue that here's actually the mechanism. A lone pair of electrons on one of the oxygen atom is picking up that. That's the mechanism for this. Yeah, and we're going to form this guy. It's dative. There we go. Remembering that the arrow tells me which way the electrons are coming from. Yeah, both electrons in that dative covalent bond. I want to move it a little bit closer. I don't want you to think that it's not a normal. There we go. It's actually bent as well, just to let you know. Yeah, this is a bent shape. There's also charges, full charges here. Okay, year 12, impress me. There are 2 full charges in this molecule. Who has them? Can you please pause the video, draw that out, and then put my full charges where they need to be, please. Pause the video, have a go. Okay, so you should have unpaused the video once you've had a go at doing this. So let's now track the electrons. So this is the pair of electrons here that's causing us problems. Yeah, and we know that at the beginning of this process, I'm just going to remove this. Yeah, there we go. I'm going to put those back on though. So at the beginning of this process, this oxygen atom here has a 100% share in 2 electrons. It owns both of them. Yeah. However, once it forms this dative, it now no longer has a 100% share. It doesn't have a 100 anymore. It now has a 50% share in the 2 electrons. That's like losing 1 electron. What that means is the central oxygen atom is now fully positive. And this oxygen here, this oxygen, had a 0% share in 2 electrons at the beginning and now has a 50% share in 2 electrons. It's like gaining 1 electron. So that one is fully negative. There we go. So there's the image that you guys had to do. That was part of an Edexcel exam paper, by the way. It gave you the process, it talked you through it, and then asked you to label the charges of the molecule. I thought it was a great question because it really does pick apart students' understandings of what happens when a dative bond's formed. Yeah, really, really clever. I did like that one, although I did think it was very hard. I mean, that is grade A level at that point, folks. Yeah, even just identifying charges like that is tough, especially in a scenario where you guys hadn't looked at ozone because it's not really part of the Edexcel specification, but they like to do it anyway. And you can see why. So, okay. So now that we've kind of had a look at what ozone is, it's nice for me to now talk to you about what ozone does. So O2, just to explain that the ozone layer has one function. The ozone layer in our atmosphere has one function, and that's to absorb UV radiation, UV light. Now, the reason why it's there to do that, folks, the reason why it's there to do that is because if the ozone layer wasn't there, then none of us would even be on this planet. Yeah, the reason being is that life came out of the oceans. Life literally walked out of the oceans at the start of our kind of evolutionary history. And one of the reasons why they could do that was because the UV light, plants, photosynthesis evolved in the oceans, and they started pumping out oxygen out of the oceans into the atmosphere. And that oxygen, of course, built up until ozone started to be formed in the upper atmosphere, which then blocked out the UV, which meant that life could actually crawl out of the oceans without being cooked. So without this atmosphere, no one can live on land. Yeah, you have to be 10 meters underwater to protect yourself against the UV light. So ultraviolet light causes damage to DNA. UV damages DNA. Damages DNA. Do I still have everybody here, or is everyone just like left it running? I feel like I'm just getting no communication from you guys. It'd be nice to have a bit of feedback. UV damages DNA, which causes cancer. So how does the ozone layer do this? Well, okay, so if you look at, again, hey Julian, oh, it's nice, thanks Nikita. Is ozone polar because of the charges, or is that why it can absorb UV? Oh, Ria, that is such a good answer. Oh, Ria, it's actually more complicated than that. Oh, okay, blimey. So ozone, that's what you get at AS level. Eek. That's Ria's fault. This is what we get at AS level, but when you get to A2 level, something else also happens. So in reality, the molecule actually goes into what's called a resonance structure. Yeah, like this, where you end up with this awkward swapping. I'll draw the two out rather than drawing the resonance one. I'll draw you this. We know that we've got the dative here, yeah, and that's now fully positive and that's fully negative, and then that's going to oscillate between this one. The double bond's going to fluctuate, yeah, and that's going to remain positive, and that now becomes negative. So it's oscillating between the two. Yeah, it's actually moving between the two of them. Yeah, and this sets up what's called a resonance structure. So you could then argue that, in fact, neither of those two really exist. And you end up with a fully positive oxygen there and then a distributed negative charge amongst it. Yes, it is polar. It's actually, by the way, that is what's called a delocalized pi system. Anyone who's interested, A2 chemistry, folks, this is called a delocalized. Can I just point out, by the way, this is beyond it's beyond A2 chemistry as well. They never go as far as this. They can't in Edexcel because you guys don't do hybridization properly, and therefore you don't do resonance structures properly, but you do cover resonance structures in benzene at A2. This is called a delocalized pi system. You do cover a little bit of this at A2 for benzene, but not in relation to other molecules, but it's great chemistry. It is polar, yes, because the molecule is not symmetrical because it's actually not linear. Yeah, so it is a polar molecule, but that's actually not why it absorbs UV light. The reason why is in order to make an ozone. So what happens is you take O2, an O2 molecule, and you hit it with UV light. The UV light breaks the molecule into two oxygen-free radicals, two oxygen atoms, which is rather tricky. Now, can I just point out, it's actually a rather complicated system here. It does create, but the problem is it has two unpaired electrons. Yeah, it creates two oxygen atoms, and those oxygen atoms now react with O2. So O2 reacts with O to form O3. I know, this is rather awkward, this. Yeah. you don't actually need to, and by the way, that reaction there, this one requires UV light as well. I know, I'm going to actually do this in a simpler setup. So O2 reacts with an O to form O. Is that what I want to do? O3. I'm going to go backwards. O3 is hit by UV light and broken into O2 and O. Yeah. And then, is that the right way that I want to do this? No, it's not. It's not. The way I want to do that, I'm going to simplify it even further, folks. Yeah. So three O2s will react to form 2 O3s. That's a better way of looking at this. So you can imagine that you've got these 3 oxygen molecules, and in the presence of UV light, yeah, with UV light giving them energy, there we go. With UV light giving them the necessary energy, these guys collide. Can I just point out, this is a bit of an oversimplification, but that they collide to form 2 O3s. Yeah, they form 2 O3s. And then once they form O3s, here's the cool bit. More UV light comes in. More UV light comes in to break it back up. So it's actually reversible. And I don't want to overcomplicate this particular process. There we go. So it's just, that's the overall equation for what's going on. Yeah. And in some regards, that is the easiest way for me to do this, just to simply describe this as a collision process. It's actually more than the collision process. There are other kind of free radical processes going on here, because it's the UV light is breaking a bond. That bond then creates oxygen radicals, which will then form dative bonds, and then they get broken back up again. I'm wondering whether or not I might get you guys to do a bit of research on this. It might be handy. But it's easier for you guys to realize that the reason why ozone is so effective is because UV light is needed. UV light is needed to make them and needed to break them. It's absorbing it in both directions. So it is an amazing UV shield. Yeah. Oxygen, without oxygen's ability to do that, folks, we wouldn't be here. And it's rather lucky that it happens to be that UV light happens to be in the right frequency to be doing that process. Yeah. And again, lucky it only happens in the upper atmosphere. Yeah, because it needs to be closer. We're in the right distance from the sun. We've got the right concentration of oxygen. This sounds stupid, but you know how O3 is heavier than most atmospheric gases. Why doesn't the ozone, the O3 like sink? It does. It quite literally does. Kayun, what a great question. So, do you remember I drew this picture here? So, also, does that mean that the atmosphere is in equilibrium? Yes! Oh my God! Yes, it is. That is exactly right. It is in equilibrium. So I'm just going to quickly find a picture on the internet of oh, by the way, did I do who was missing? Did Emma ever turn up? No, haven't seen Emma at all. Brilliant. Thanks, Emma. Let's do Earth atmosphere composition. I want layers, really. No, I don't want composition. I want layers. Layers. Like an onion. Yeah? The Earth is like an onion. Mesosphere, thermosphere, exosphere. Yes, that's what I want. But I actually want, of course, to see where the ozone layer is. There it is. It's in the stratosphere. I thought it was higher up than that. Not exactly sure I trust that one. Yeah. I don't mind it, really. Can. Ozone layer, top of the strato. Yeah, okay. It seems to be bottom of the strato. Okay. Oh, fine. Can. So here's our atmosphere. What you realize is, by the way, guys, that 95% of the air is in the troposphere. So that's like way down there. And the stratosphere, mesosphere, thermosphere. I've forgotten all my spheres. But you can see where the ozone layer is. And it's a layer. So just to answer your question, Kayan, so the reason why the ozone has this particular layer in the atmosphere is because of the change in molecular weight. Yeah, because when O2 rises, it reaches the top of it. Yeah, the O2 here, it gets hit by enough UV, becomes O3, and then sinks down to, and by the way, within this narrow range, within that narrow range is enough UV light to split it up and turn it back into O2. Yeah, so it lives within a particular region that has a very distinct layer, all because of this idea of the equilibrium and its balance between its molecular weight. If it wasn't, it would be a much skinnier layer. And we're quite lucky that it's not. Yeah, it's quite a big difference in weight. You're moving from an MR of 32 to an MR of what, like 48? Yeah, and so that's much heavier. So yes, it forms this layer because of its molecular weight change. Ria, you're absolutely right. This part of the atmosphere is in equilibrium, and this is a problem. Yeah, this is a problem. Because in fact, we can actually talk a bit more about the ozone layer. And by the way, this is commonly done because they can use this as part of your equilibrium topic of equilibrium and AS. So would anyone like to fathom a guess as to which one of these arrows is exothermic and which one is endothermic? Don't overthink it. Which one's endo, which one's exo? Have a guess. See how many people are still here and they're not just playing it on the laptop and wandering off. Lol. Forward exo. You think the forward is exo, Dana? Why do you... Right is endo. Can't say left or right here. It doesn't really help me, guys. Do you mean forward or backward? This way? Because if you're going to go left, you'd have to say left to right. You can't just say left. That's not an arrow, folks. Come on. Yeah, you've got to remember, if you're going to do left and right, you must forward. Okay, so forward endo. So let's consider what's happening. I've got 3 molecules. I've got 3 particles. Yeah, and I'm now creating 2 particles. Yeah, would everyone agree? I'm making bonds in this direction. 3 are becoming 2. Yeah, so we've got a mexo. Making is mexobendo. Making is exo. So this is exothermic. And then we're going to take 2 particles, and break them up into 2. So we've got the backward one is endo. Come on, folks. Mexobendo. Yeah, forward. Why do you think the forward is endo? Mexobendo. Yeah, mexo. Making is exo. 3 particles becoming 2 particles. They're joining together, yeah, making bonds, yeah? But then if I take 2 particles and I break them up, I'll break them into 3 and breaking bonds, yeah? Mexobendo. Forward reaction is exo. So that was a bit of a disaster, wasn't it? Everyone got it right? Guys, you're better than that. Mexobendo. Bonds, take 2 and break it into 3. Oh, anyway. That didn't go very well, did it? So, and this is why I'm doing this, folks, just to remind you. Yeah? So, by the way, there's not a huge energy change in this, but there is enough. What that means is, so if that's the case, yeah, if we are busy, guys, we are busy going through global warming. What's happening to the temperature in the atmosphere, please? I hope you guys are going to realize how far global warming goes and the fact that you guys have no idea how deep this runs. What's happening to our atmosphere, folks? It's rising. Brilliant. Increase temperature. Increase temp. Right. What effect is that going to have on that equilibrium? Yeah, you should be worried. What's happening to that equilibrium? Go on. Come on, guys. Who's going to get it? Shifts to the left. Well done. And what does that mean in terms of the quantity of ozone in the atmosphere? You're right. More O2, but I don't care about the O2, do I, Ria? I care about the ozone. Because what's the ozone doing? Protecting us from UV light, which is stopping us getting cancer. What's happening to the quantity of the ozone? It's decreasing. Yeah, guys, does everyone realize just how bad global warming is? Yep, you got it, Ria. So less UV light is going to be absorbed, which means there's going to be an increased rate of skin cancer. Before you know it, guys, you're going to be wearing factor 100. Yeah, this is not good. The ozone layer is thinning because we're warming our atmosphere. The only people who understand global warming are chemists. You guys have no idea how deep this runs. It's scary, man. Yeah. Oh, so worrying. Carbon dioxide, we're going to ruin this planet. We're not just going to ruin it. We're going to just utterly I'm just going to stop. Sorry, folks. Sorry. It's very depressing, isn't it? Let's not talk about that. Yeah. Oh, dear. Right. So let's just avoid global warming for a minute because it's upsetting me. So, okay. The next thing is, so we now realize just how much we care about the ozone layer. It's awesome. It protects us from the sun. It means that you guys can go outside without getting skin cancer immediately or being sunburnt to a crisp. So the question is, why is this a topic on AS chemistry? The reason being, folks, is because I think everyone here has heard the fact that, we're destroying the ozone layer. Yeah. Well, the reason why we're destroying the ozone layer is because of, can everyone put a little title of CFCs? And this stands for chlorofluorocarbons. CFCs. Yeah. So CFCs, I'm going to tell you the most famous. CFC number 11. Trichlorofluoromethane. This is CFC 11. I know, right? They're given names because there's loads of them. Loads and loads and loads of them. So we've been making these compounds, these CFCs, for years. In fact, for decades. And there's a reason why. The reason why we make these compounds is because, number one, they are non-toxic. They are non-toxic. You can breathe these all day long. Number two, they are inert. They're then unreactive. This is good. And number three, they have boiling points. And this is really the reason why we've been making them. Boiling points of around room temperature. Room temp. Okay, so people often then say, well, why is that such an important thing? Yeah, why do we care? The reason why we care is because of refrigerators and air conditioning units. Yeah, you guys don't realize how do you cool something? Now, I don't want to get into refrigerator technology. I would if I was in class, and I'd even show you it working. But when there's a change in state, when a liquid boils, when a CFC liquid, by the way, it's any liquid in reality, turns into CFC gas, yeah, there is a decrease in temperature. Decrease in temp. Now, just to tell you why, you know this, because if you spray, do you know if you put you're inert? Whoa, Julia just reacted. Decrease in temp. Why? Because we're breaking bonds, folks. Yeah? In this direction, when we're a liquid, we know that there are forces, weak intermolecular forces between particles. Yeah? Well, we're going to break those. We're going to turn it into this. You break bonds, that's endo. Yeah? Mexo-bendo, breaking bonds. Which means if you go from a liquid to a gas, the temperature, this is what happens when you spray your deodorant under your arms, folks. Yeah, you go from a liquid in the bottle to a gas and it gets cold. Well, this is what's happening in your refrigerators or in your air conditioning units. I shouldn't use fridges. I should always use air conditioning units in Malaysia. The reason why is what happens is in your air conditioning unit, yeah, in your air conditioning unit, there is a reservoir, a pool of liquid, well, by the way, it used to be CFCs. They're meant to be banned. Can I just point out, by the way, more than half of you in this room right now will currently have CFCs in your air conditioning units because it's cheaper. And people often turn up to their houses to refill them and goes, do you want to use cheap gas or do you want to use expensive gas? And everyone goes for the cheap one, and that's a CFC because it's illegal. Yeah? So you have a pool of liquid CFC inside your air conditioning unit. And then what happens is it goes through a little set of tubes. And what happens is it boils. It goes through these tubes and it boils. That's why you hear a gurgling sound. Yeah. So during this process, when it's going through these tubes, it's turning, and at the end of it, it comes out as CFC gas. Now, how do you then turn that back into a liquid? What you then do is put it through a compressor. So this is just a little motor, a compressor. And that compressor takes the gas and squashes it back down into a liquid. And then they put that liquid back into the reservoir. Isn't that neat? So all you need to make an air conditioning unit is an electrical pump, an electrical compressor, and a reservoir. That's it. That then gets plugged into your plug socket. Yeah. So the pump, that's why every now and again you'll hear your air conditioning unit or your refrigerator go, as the pump turns on. Yeah, it was a terrible impression, or just as the little compressor takes all that gas and turns it back into a liquid and shoves it back into the reservoir. That's all it's doing. It's really clever. Works really well. And so this is how we cool stuff down. This is how your refrigerator works, how your air conditioning works. It's how lots of things cool stuff down. Yeah, just changing state. But you need something. You need a gas that can be easily turned into a liquid and then turned back into a gas when exposed to warmth. CFCs fit the bill. Now, there's a problem, though, because they didn't realize this when they first created them. Because they said they're inert. These guys are non-toxic and inert. Oh, by the way, they're also not flammable. Non-flammable. Yeah, that's great. You can't burn these things. Yeah, these guys are awesome. We love these guys. We love you. Love you, CFCs. And then they realized that the problem is, you see, they were using these not just for refrigerators. They used to use them in your deodorant cans, in your hairspray cans, anything that required a compressed gas as a propellant was ideal. This is great. But there's a problem. So let's now look at this. So what I'm going to do is here's our planet. Yeah, this is our planet. And we're going to there we go. Let's put Nikita. Yeah, let's put Nikita on planet Earth. There we go. There's Nikita. Now, Nikita loves to make herself look pretty. Don't you, Nikita? Is she still in the room? I hope she is. She's still here. Oh, dear. Where is she? Come on, Nikita, where are you? I've lost her. Down to 10 people. People keep wandering off. Oh, boo. Fine. I'm going to replace it with, let's make it, shall we make it Dat then? Should we make Dat? Yeah, Dat loves to make himself look pretty. There's Dat. There we go. Look at his hair. Looks cool, doesn't he? Now, what Dat loves to do is he loves to use his hairspray. There we go. Loves to use his hairspray. Yeah, Dat, you're in. You've got awesome hair, dude. I love you for your hair. So I'm putting you on the planet. Yeah. Why is Dat so big? Yeah. It's not to scale, all right? So Dad's using his hairspray, and his hairspray, of course, is putting out loads of, this is back in the old days, by the way. This is in the 70s and the 80s. Yeah, the hairspray increases the volume of his hair. Yeah, that's correct. And he's pumping out a whole load of CFCs into the air. That's what used to happen. Yeah. And what happened was those CFCs would travel up into the atmosphere. Yeah. It would travel up into the atmosphere until it reached our good old friend, the ozone layer. So here's our ozone layer here. So the CFCs are going to float up because, of course, they've got, I mean, don't get me wrong, they're heavier than air, so they stay down. They stay at the lower atmosphere most of the time, but the air is moving. It's constantly in flux, so which means some of it floats up into the upper atmosphere. And what now happens is the CFCs reach the ozone layer. So the CFC number 11, I'm going to shrink this as best I can. CFC number 11 gets to the upper atmosphere, still totally fine, non-toxic, inert, yeah, gets to the ozone layer, floats into the ozone layer. So here's CFC 11. Yeah, floats into here, still totally fine. And then it reaches the very top of the ozone layer. Now, what you'd hopefully all realize here, folks, is that as you move through the ozone layer, I've suddenly realized I've not done as much as I wanted. As if you imagine this is our ozone layer. Okay. This is our ozone layer here. Yeah. The UV light from the sun is crazy intense at the top of it because none of it's getting filtered out. But then it hits O3. This is the ozone layer. And what happens is as you move through the layer, it gets filtered out. Yeah, as you get lower down, yeah, it gets more and more absorbed until eventually only a tiny amount of it trickles through onto this side. And this is the stuff that gives you a tan. Yeah. So the UV light that went in is intense up here and very low intensity. Yeah, that's high intensity. High intensity, and this is low intensity. So what now happens is our CFC number 11 comes into the atmosphere here, and it floats up until it gets to about this point in the ozone layer, where the intensity increases, then something really bad happens. Here's what now happens, folks. Hang on. Here's what now happens. The UV light causes something very bad to happen. The UV light, which is increasing in intensity, splits a bond, and it breaks the carbon-chlorine bond. And it breaks it homolytically, like that. And I create 2 free radicals. This is a problem, because one of those free radicals loves ozone, and it's the chlorine one. This one is about to cause a whole load of problems to our ozone layer. Here's what now happens. That Cl dot, which has just been created, now collides with an O3. And what's it going to take? It's going to steal an oxygen atom, and it's going to form ClO dot and oxygen gas. So I can explain to you why that becomes a free radical if you want me to. Just to explain, here's what's happening. Here's the chlorine free radical, otherwise known as a chlorine atom. There's its free radical. Yeah, it's unpaired of electron. Yeah, here's ozone. Here's ozone. Yeah, and what it's going to do is it's going to steal an oxygen atom. Now, if it steals an oxygen atom, how many electrons does it need to take? Anyone like to guess? It only needs 1. Let's say it takes this guy. Yeah. In fact, no, let's not do that. Let's take this one here. Yeah. So actually, no, I'm not going to bother doing that one. I'm going to just draw a generic one. So here's what's going to happen. That chlorine is going to form a bond with oxygen, but it only needs one electron to fill that space. So it's going to form a single bond with it. So there's the chlorine atom that's formed a bond. And here's the oxygen atom. How many electrons did the oxygen atom have originally? It had 6. Now here is one of them. Here is one of those. Let's show the other ones, shall we? 2, 3, 4, 5, 6. The oxygen has an unpaired electron. So it becomes the free radical. Right, now once that's done that, I've now created a second free radical. Guess what that free radical can now collide with? It now collides with another ozone. And it turns it into Cl dot and 2 O2s. Right, let's have a look at these equations next to each other. Sorry, I'm going to get rid of that because you really don't need it. As long as you can remember that it forms a chlorate free radical. How am I doing for time-wise? I'm nearly over. Guys, can someone tell me, number 1, what is the role of this guy? What is the role of him? What's the role of the chlorine free radical? Let's see how many people are still watching. I can't imagine it's many. People are bored and have left, I feel. Sorry about this, folks. Can anyone tell me? Well done, DAT. It's a catalyst. It's provided an alternative reaction, but itself not used up. Right, guys, let's now create the overall equation for this. Can everyone pause the video and put these two, please, together? What do you get? What do you get? And that's the problem. These equations come together to form one equation which destroys ozone. This is the destruction of ozone, folks. The ozone is becoming oxygen. So CFCs, the problem is it's even acting as a catalyst. That chlorine free radical right there, that chlorine free radical will destroy 100,000 ozone molecules before it's removed from the system. That's terrifying. So we've been busy eating a hole through our ozone layer because of CFCs. So CFCs have since been banned. They're still used, though, illegally. Every time you fill your air conditioning up, guys, please make sure you pay for the more expensive stuff, because that stuff is CFC free. It's a bit of a nightmare. It destroys ozone layers, and it's a catalyst. Great free radical processes going on. We've got an initiation step up here. That there is an initiation step. We've got 2 propagations. We've got an overall equation for the destruction of ozone. Even though this is not on your specification, I totally understand why they were able to ask it. And they do. As I said, they've only done it once, but they can. Yeah, what they did was they gave you this equation and asked you to draw the arrows for it. Yeah, they gave you that one. And they gave you this, like that, and said, draw the arrows showing the type of, and then give the name of the type of fission. Australia has a hole in their ozone layer, RIP. Yep, they do. Yeah. Guess who uses the most air conditioning? Yeah, exactly. Exactly. Anyway, right. So just to point out, by the way, there are other gases as well which do it. Look them up. Nitrogen oxide as well. It's a bit of a nightmare. Here's another one. NO and NO2. These gases are problems. Yeah, because what they can do is they can move between the 2 states. So O3 will react with NO to produce NO2 and O2. Yeah, and then NO2, and then NO2 can react with more O3 to form NO and two O2s. This is a nightmare. The nitrogen oxides doesn't just contribute towards acid rain, it also contributes to the destruction of the ozone layer. Nightmare. Absolute nightmare. Problematic. Anyway, I've realized it's the end of the lesson. In terms of my learning objectives, I've just covered the first one, understanding FRS and ozone problems. I will pick up this lesson next time, and we'll look at EA, major minor products, and elimination products. We will do that. I might do some webinars over Easter if you guys want me to. I'll communicate that with you later on. I'll leave you on today's lesson. Let's see if I can get back to my screen. Want that one? Go for that one. Hey guys, right. I will leave you be today. Have a look at the ozone questions on the in free radical substitution and the haloalkanes booklets on the worksheet. Please have a go at them, Year 12. You are probably going to have, when we go back to school, I have finished Unit 2. You are probably going to be having another mock, yeah, when we go back. So please make sure you're using the document and doing some questions. Dana, you are so welcome. Kayun, you're welcome. Ria, you're welcome. It's been so great to see you guys. I'm going to miss you guys over the Easter. Make sure you keep working hard, guys, and taking care of yourselves and being safe. Have a nice Easter, folks. I'll see you in a couple of weeks.